Bingo. Okay, tonight we're going to concentrate on understanding the central limit theorem and understanding the idea of a 95% confidence interval and what that means. Okay, and I'm going to go through probably the uh, 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 the class session for the first hour or so, and then I'm going to stop and we're going to maybe go over parts of the exam that were problematic for people, so we can actually do a little review of that. And if I don't get enough time, or if I don't, my battery doesn't last long enough to do much of that, I'll switch to another computer and pick it up, or I'll schedule an extra session, like an online session, where we can just devote ourselves to the exam and go over all parts of the exam. Okay, so I want to get started on this idea of the central limit theorem. You guys might have remembered that, well, first of all, number one, you remember the empirical formula, right? The empirical formula tells us that there are certain properties about a normal distribution that are common to all normal distributions. The relationship between the mean, which is the middle, and we're going to start to call it the point estimate, the middle point, the middle of the distribution, the average value, the median value, the middle, right? We're going to call that a point estimate, an estimate of where the middle of the population is. And up till now, we've been talking about this idea of knowing the mean for the entire population, mu, knowing the standard deviation for the entire population, sigma. That almost never happens, right? We usually have to deduce that from a sample. In other words, we start out knowing nothing about the population, we sample the population, we find the average, we find how variable it is, and we calculate standard deviation. So now we say from that sample, we know something about the population. Okay, problem with that is that we could do that once and get a number that's very close to the population mean. Then we could do it again and be below the population mean. And we could do it again and be above the population mean. We'll never know for sure how close we are, right? Because we don't know the population mean. We're never going to know it. What's the average height of every student in Hunter? Well, unless we go and measure every student in Hunter, which we're not going to do, we're never going to know that. So we could take a sample of 100 Hunter students, find the average of those 100, right, and say, that's a pretty big sample, 100. Yeah, and you'll find that as we go forward, we're going to talk about sample size. But a sample of 100 is a pretty big sample for something like that. Okay, so, and then we'll say, well, the average height that we got was 5'6". And we might say to ourselves, that sounds like it's pretty close to what we think the average for the entire student population is. But we have no way of knowing what it really is unless we calculate everybody. We could get a better idea maybe by increasing the sample size, so we have a little bit more confidence in what it is. But you even know that if we did that with 100 students, found a mean, if we did it again, we'd find a different mean. Maybe the next time we'd find 5.7. Maybe the next time we find 5.5. So we have to accept the fact that we're never going to be absolutely certain what the population mean is. However, because we understand how normal distributions work and how sampling works, what we can find out, and what we're going to learn about tonight, is that we can understand what the range of probabilities are for the true population mean. In other words, if we sampled 100 students and we found that the average height was 5'6" tall, and then we looked at those 100 students, we found that the shortest person was 5'4", and the tallest person was 5'8", we'd say to ourselves, gee, it's very narrow distribution, it's very tight distribution. I can have a pretty good idea that I'm pretty close to the true population mean. But if the shortest person was 4'8" tall and tallest was 6'8" tall, it's much more variable. So I'm not as confident that I'm very close to the true population mean. So what we want instead is when we take a sample, we calculate a mean, right? We want to be able to say, what's our level of certainty what this mean really is? So that's what the confidence interval that we talked about last week, that's what that's going to do for us. In other words, if we find that the mean is 5'6", right, based on the variability, then we can say, I know that I know from what I know about standard deviations and the normal distribution. I know, and we know that taking repeated samples, we can generate a new normal distribution, right? And that new normal distribution has a new standard deviation. We call it standard error. And based on knowing what that is, standard error based on our calculations, knowing what that is, we can say to ourselves, well, based on the normal distribution, even though I don't know, even though it looks like to me it's around 5, 6, and I don't know exactly what it is, I can give myself a range of probabilities so that I can get a lower number and a higher number and say I'm 95% sure that the real population mean is between these two numbers, right? So there's a lot of power to that. I can't say I don't know if it's the low end or the high end, but I know with 95% certainty it's between these two numbers. And if I'm willing to accept a lower probability, like say I want to be 90% sure, I can have a wider range, a narrower range for that. If I'm willing to be only 90% certain, if I want to be 99% certain, well then I have to have a wider range to make sure I capture the true population mean between those two. So when we're going to calculate confidence intervals, we're going to calculate several different confidence intervals. We might want to be 95% sure, and 95% confidence interval. We might be 99% sure, we might be 90% sure, or even less, let's say 60%, 70% sure. We could calculate any interval we want. Okay, but the level of certainty that we want to achieve is going to affect the width of that interval. And we're going to see that there's a formula that's going to help us calculate that. And you'll see how it accommodates the width of the confidence interval to the data that we have. Okay, and we're going to be working with that formula shortly. Okay, you guys okay online? You following all this? Okay, so this is standard normal distribution. We know about 68% of it is one standard deviation below the mean, one standard deviation above the mean. We know that 95% of it, approximately, is between two standard deviations below the mean and two above the mean. And almost all of it, 99.7%, is between three standard deviations below and three above. Okay, so I might have a population like the one I just described. I might have a population where the distribution looks like that. I don't have my pen, so it's going to be a little bit sloppy, right? Where I know that this is what my population might look like. I'll never know the real distribution because, yep, there's a problem there. Oh, yeah, for you guys, hang on a second. Let me move this out of the way. Oops. I'm going to need that later on, so that's why I'm not minimizing it. How's that? I guess you can see that. Okay, so now if I take a sample of size, let's say 25 from this population, and I repeatedly take that sample, right? Well, the mean of that sample is most likely going to be pretty close to the distribution that I have for the population. In other words, my expectation is that if the mean of the population is 100, if I take 25 people, find the average for the 25 people, I'm going to get around 100, right? In other words, doing that, the sample mean approximates the population mean. But now if I took 25 people over and over and over again, found the averages, and I use those numbers, those new means for each one of those samples to create a new distribution, well, the mean would be in the same place, but the distribution would be narrower than the population mean, the population distribution. Now, if I took a sample size that was even bigger, a sample size of 100 people in each sample, well, each one of those means are going to be closer to the population mean. It's going to be even a narrower distribution, right? So that might look something like this, right? So the bigger the sample size is, the narrower my distribution is, which means my standard deviation is smaller, it's a smaller number. Because the standard deviation is a measure of the variability, basically, of the numbers that you're looking at. Okay, so in order, let's pick up from from this exercise. There's two documents here. One is how to calculate a confidence interval, right? We're going to hold on to that because that's going to be kind of a summary document for you. I'm just going to open it up just so you can see what it looks like. Okay, and this is kind of like a step-by-step rule on how to actually do this process, right? And you can refer to this as you work with the various homework examples and so on and so forth. The one I want to open now and actually work with a little bit is this one, this PDF file. And in fact, actually, I think I got a Word version of it. I'm sorry I didn't post the Word version of it. PH750. Yep, that's it, I think. No, that's 15, but 16. PH750. Let me see all of them. Okay. Underscore 6 dash 22 dash 16. Here we go. Okay, so I'm going to take a look at this and I'm going to actually run through some calculations now. Okay, first of all, the mean of a population is 160. We know the population mean. Standard deviation of the population is 20. We know the population mean. Standard deviation, artificial situation, we usually don't know that. What would be the probability that a single observation selected at random from the population would have a value of less than 154? Well, in order to calculate that, I'm going to open up Excel. Okay, and forgive me for using Excel. You don't have to use Excel if you're allergic to it. Okay, I know that's an issue sometimes, but I think you'll be able to follow. It'll speed it up for us, and I think you'll be able to follow it anyway as I go through it. So let's see. The mean mu is equal to 100. What did I say? 160, right? The standard deviation. Whoops, I should go up here. 160. The standard deviation sigma is equal to 20. And the value I'm interested in, x, right, x is equal to 154. I want to know what's the probability that a single observation selected at random would have a value of less than 154, would be to the left in the distribution of 154. Okay, so the way I would calculate that is I would calculate a z-score, right? Z, what's z going to be equal to? Z is going to be equal to x minus the mean, mu, right, divided by the standard deviation, right? So z is equal to minus 0.3. Okay, so now I want to know what area that is. It's a little bit to the left of the mean, right? So in other words, it would look something like, let me get back to this. Nope, where'd that notepad go? Okay, it would look something, if this were 160, right, and standard deviation was 20, it would look something like this, and we would be interested in this area in here, right? So it's going to be less than 50%. We know that. So I'm going to open up Agresti. Okay, again, in case you don't like using the Excel for the areas. I'm going to open up Agresti and look for the area to the left, like as it's shown in the diagram, the area to the left of the z-score of 0.030, and it's 38.2%, 0.328, right? So that area is 38.2. Okay, so, let me go back to our home problem there. Okay, so that would be 38.2. What's the probability that a single observation has a value greater than 166? How will we figure that out? Well, we do exactly the same thing, right? Except now the x value is 166. Okay, mu is still 160, right? Sigma is still 20, except this time we're interested in the area to the left of, what did I say, 166? So z is going to be equal to, I'll put parentheses in ahead of time, minus 160. It's going to be a positive number now, divided by 20. and it's going to be equal to plus 0.3. Okay, and plus 0.3. If I go, I'm going to do one. I'm going to do it in Excel this time. This one was 0.3. What was it, 0.328 or something like that? I forget. 0.382. 0.382. Okay, and this time the area to the left of 166 is going to be equal to norm inverse, norm S dist, right? If I use norm S dist, I'm working with the standard normal distribution, and the only thing it's going to ask for is the Z-score, which I've calculated. Okay, and I'm going to hit, did it get it? Oops. Let me try this again. Equals norm S dist, parentheses. I'm going to look up, see if there's any questions in a second. All it asks for is a Z-score, and you hit enter, and the area is 0.618 approximately, right? So that's the area to the left of this. That's the percentage, the probability that you randomly selected person would have a value below 166. So what's the probability a single observation has a value between the two of them? Well, then what I'm doing then is I'm just simply going to basically subtract one from the other. In other words, this would be 166, and it would represent the whole area from here to the left, and the negative 0.3 Z-score, the area from there to the left. So if I just take the larger number, subtract a smaller area from it, it'll leave the area between the two, which is what it's asking me for. You guys all comfortable with that? Are we happy? Yes? Yes? See, I can't see their faces there. So I have to depend on you to give me some reaction. Okay, you guys are okay with it too, right? So the area then is going to be equal to, and I'll come back to it. It's going to be equal to this minus this, or about 23.6%, 0.236. Okay, so now that's the way we'd work with the normal distribution. So now let's move on and see what we could do when we start to work with samples. Now, I'm going to do something, you're going to see me do something that's a little weird right now. After telling you, we're never going to know, for the most part, never going to know what the population mean is, what the population standard deviation is, and so on and so forth. I'm going to tell you that for our purposes today, we're going to make believe we know the population standard deviation. The reason why I'm doing that is because when we do these analyses, if we are working from a sample, we have two areas of uncertainty. We calculate the mean, but we don't know that that's exact, right? There's a certain uncertainty. Is the mean above or below that? And there's also, if we use the sample to estimate the population standard deviation, that's also uncertain, right? We could be too low, we could be too high. So right now for tonight, I only want to work with one bit of uncertainty. So I'm going to say the mean we're not sure about, and we're going to calculate confidence interval, but I'm going to make believe I know the standard deviation for the population. When we get into next week, we're going to find out ways, even like maybe before the end of the night tonight, we're going to start to talk about how do we adjust for the fact that we don't really know the population standard deviation. We're just estimating it from the sample that we have. Okay? So we'll get to that. I'm sure we'll at least mention that tonight. We'll at least bring that up. Okay, let's take a look at the next sample, see if it's a little bit different. A random sample of size n has a mean of 150. What happened now? We're not dealing with a population anymore. We're dealing with a sample, right? Things have changed now. So the mean of the sample is 150. Do we know is that the population mean? We're hoping it's a good estimate, but we don't know what the population mean is. Assume that the population is normally distributed and has a standard deviation of 30. As I was mentioning, we're gonna take that for granted for now. Calculate the standard error for samples of size n equals 100. What do we mean by standard error? What we're saying is if we took samples of size 100 over and over and over again and created a new distribution, what would be the standard deviation of that new distribution of all the sample means? Instead of calling it standard deviation as sample means, we're calling it the standard error. Okay, and you guys remember how we calculate standard error, right? Standard error was equal to, right, yeah, let me see if I can't write it actually. I'll give it a try. Okay, there's a normal distribution. Okay, and the standard error is equal to, is sigma, population standard deviation, which presumably we know, over the square root of the sample size. So remember what I said about the sample size gets bigger, our certainty gets like our range and for that mean, the true mean gets narrower and narrower. Well, that's because the standard error gets smaller. In other words, our variability gets smaller as the sample size gets bigger because it's in the bottom of the fraction, right? The bigger the number gets in the bottom of the fraction, the smaller the bigger this number gets, the smaller the fraction becomes. Okay, so smaller is, yep. Let me stop talking so I don't mix it up. Okay, so let's calculate standard error for a sample of size 100. So it's going to be equal to, let's see, sigma is 30, right, divided by 30, divided by the square root of the sample size, which is square root of 100 is 10. So the standard error is equal to 3. Okay, so let's take a look at the next one. Compute a 95% confidence interval for the mean of the population. Okay, so now how do we do that? We're going to want to know, since we have a new distribution now, right? We have a distribution that has a middle at 150, right? Our distribution has a middle at 150, a mean of 150, and it has a new standard deviation, a standard error, which is equal to 3. So if we're going to consider if we took samples over and over again, we would expect those samples to 95% of those samples to fall within 2 standard deviations below the mean and 2 above the mean. Except I'm not going to be cute anymore. Before, remember we said that with the empirical formula it was about 2 above and below. Well, in fact, remember we looked at the Agresti table, and in fact, the 95% interval is really represented by 1.96 standard deviations or standard errors, minus 1.96 and plus 1.96, right? Close enough to 2 that like a lot of times you can just use 2, but it's really 1.96, right? So let's see, compute a 95% confidence interval for the mean. So now in order to compute the confidence interval, what I'm going to do is I'm going to take my mean, which I just calculated, x bar, and I'm going to add or subtract, right? I'm going to do it both ways. Add or subtract 1.96 standard errors, right? Times the standard error, right? I'm not going to try and draw at, maybe I can, right? Times 1.96 times the standard error. So in other words, if the standard error is 3, I'm going to subtract 6 from the mean I calculated and add 6 to the mean I calculated. So I wind up with 2 numbers. When I'm going to use 2 for the moment to make it simple, right? So it's going to be equal to 150 minus 6, right? It's going to be equal to 144. Right, that's 2 times 3, or 1.96 times 2, 144, and I'm going to add 6 to 150, 156. So we now have a range of outcomes here. 2 standard deviations below the mean, 2 standard deviations above the mean, as represented by the values 154 for the sample means, up to 156. So now, what we can say is, at this stage, we can say to ourselves, well, basically what this tells us is we're 95% confidence that based on these repeated samples, that we're 95% sure. It doesn't tell us that the mean is closer to this or closer to this. We really can't deduce that yet. But what it does tell us is that we can be 95% sure that the true population mean is between 154 and 156. That's a confidence interval. In other words, I might report it like this: 95% confidence interval is parentheses 144, comma 156. Now, does that tell us what the population mean is? No, but at least now, before, when we got the number 150, when we got the number 150, we didn't know how dependable that number is. We didn't know if we got 150 now, but it's so variable that maybe the true population mean was 130 or 170. We had no measure for how certain we were or how close we were to the true population mean. But now at least we have a range within. We can say with 95% confidence that the population mean is within those values, right? So, but that's a good thing because it allows us to deduce a lot of stuff about the population. So let's go back and pick up where we left off here. Now compute a 99% confidence interval for the population mean. Well, how would I do that? I'm going to pull up Excel now for this. Okay, now compute a 99% confidence interval. Well, what was X bar? X bar was 150. The standard deviation, sigma, was, what was it again, 30? Yep. The sample size was 100, right? We calculated our standard error, right, which was equal to, I'm going to do it again, was equal to sigma divided by the square root of the sample size. Oops. Yes, whatever it said, came out to be 3. And okay, so now we want to be 99% certain we capture the mean. Now, would you say to raise our level of certainty, would we want to make our lower limit and upper limit wider or narrower to be 99% certain we captured the mean? Got to make it wider, right? And how is that going to happen? Well, when we were looking at a situation where the number of standard deviations that we were using to subtract and add to the mean we calculated, X bar, when we were looking for 95% confidence interval, right? We were using equal norm S dist for a minus 1.96, right? Okay, that gives me 2.5% at the lower end of the curve and 2.5% at the upper end of the curve. So I know that for 95%, I'm going to use a value for Z of 1.96. Okay, well, how about 99%, right? What area is represented by 99%? 99%, I'll put that in there. What area does that have to be? What does my Z-score have to be? Let's see. The area to the left and to the right, the tails on both ends, since it's symmetrical, has to be a Z-score, which will give me a 0.5% at one end, 0.005, and 0.5% on the high end. So what Z-score is that going to be? So that Z-score is going to be equal to, and I'm going to use norm S inverse. And norm S inverse asks me for the p-value, right, the probability area, and I'm going to put in the value, I'll put in the value minus 0.005. What Z-score gives me that area for that little tail? Whoops, I made a mistake there. What did I do? Norm S inverse. Probability. How about if I just put in 0.005? Okay, it gives me a value of 0.25. I'm going to round it off to 2.258, right? So the area is, the probability is non-negative. That's why I put a negative sign in there. An area or probability is never negative. It doesn't make sense. What's the probability? Negative point. It doesn't mean anything, right? So I didn't. It's actually a negative Z-score because I put in the Z-score to the left. If I had put in equals norm S inverse, if I had put in 0.9 995, it would give me a positive z-score. The area to the left of that now is going to be what I need to, yeah, that'll give me a positive z-score, okay, because that's the area to the right. Okay, so that's the value for that I would multiply the standard error by, because I need it for 99% confidence interval, I have to be 2.58 standard deviations above the mean and 2.58 standard deviations below. So what that would be equal to is instead of, so what our confidence interval would be there, now I'm going to calculate my confidence interval. My confidence interval is going to be equal to x bar, and I'm going to add and subtract plus or minus, right? The whatever this z-score is that I need, right, in order to get that value times the standard error, right? So if I want to calculate it for a 99% confidence interval, it's going to be equal to my mean, which was 150, minus, I'll start with minus, right, 2.58 times my standard error, which was equal to 3. Okay, and it comes out to be 142.26. And my upper limit is going to be equal to, I'm going to do it again, x bar is 150 plus 2.56 times, let's see, 3. Oh, what did I do there? 2.58. 2.58 times 3 is equal to 157 points. So our confidence interval, which before was, I think, 144 to 156, something like that, our confidence interval now is a little bit wider. So now we're 99% certain the true population mean is between these two numbers. That's basically how confidence. Now, if I wanted to do it for 90%, well, what would I use that 90%? I would use, well, I'm gonna look it up a different way. I'm gonna go to the Agresti, the t-table, the z-scores, and let's look up what area. That would be 5% at the top end and 5% at the bottom. So what z-score would represent an area of 5%? So we use the area inside here for the areas. So let's see, 1.6. This looks like the closest, so it's 1.64, right? So if I'm looking for 90% confidence interval, I'd be using a z-score of 1.64. Okay, I'm gonna replace this with 2.58 just so we can look at it a little bit easier. Okay, something happening behind me? Is it working there?
Yeah.
Oh, okay, good. I know you're pointing. So, okay, so the thing that determines how wide this confidence interval is it's determined by the standard error, right? And that's determined by the standard deviation of the population and the sample size, and it's determined by the level of confidence that we want is also determined by the z-score for 95%, 99%, or say 90% confidence interval. So that's really what drives this whole thing. Okay, so now let me see where I can go with this. Now let me ask you something. I'm adding z times the standard error to each one of these to the mean each time, right? Well, what is that? Let's see what that number is. That's equal to I'm going to do it for 95%. This is the 99% confidence interval, so I'll just do it for that since that's on what we have here. 2.58 times the standard error, which was 3. I'm adding and subtracting 7.74. And adding and subtracting it, depending on to get the lower limit and the upper limit for the confidence interval. What do you think a good name for that is? Well, if I told you, I think that guy's about 50, plus or minus 10 years. Margin of error. How about calling that margin of error? We'll call that the margin of error. Right? Okay, that's a good name for that. Okay, so really, that's really what we're doing. We're creating a margin of error for ourselves for the population mean, based on our sample and our knowledge about the normal distribution. Okay, so are you guys okay with that? Online, I'm talking about? Pretty clear, right? I hope that's clear anyway. Okay. Well, we're going to have an enormous amount of power from this. Okay. Random sample. Let's move on to, let's see, let me find a good one here. How are we doing on power? We're okay. Compute a 95% confidence interval. This next one, the mean of sample size is 36, mean 150, so on and so forth. It's just a bigger sample size. And if you work this out on your own, you're going to find that the sample size is going to influence the calculate for the standard error. It's a smaller sample, right? So the standard error is going to be a bigger number. Since the standard error is going to be a bigger number, you're going to get a wider confidence interval. So since we always like to have more confidence, we want to have a higher level degree of confidence. Bigger samples are better for us because they help us narrow that confidence interval. Okay, so that's a good thing for us there. Suppose we want to estimate the average weight of adults and we want randomly sample 1,000 men in a population of 1 million men and weigh them. Find the average man in our sample weighs 180 pounds. The sample is very large, so we're going to assume for the purposes of this analysis that the standard deviation of the population is 30 pounds. Now, what did we do there? We pulled a cute little trick there. This is kind of a situation where, kind of like a real situation. We don't know the average weight for men in DeKalb County, and we don't know the standard deviation of the weights, sigma, the true population standard deviation. So in order to calculate a mean and a confidence interval, we're going to say that our sample is so big that the standard deviation of the population of the sample is an accurate measure of the standard deviation of the population. So we're going to say that it's equal to 30 pounds. Okay, and how would we work with that? 95% confidence interval. Well, n is equal to 1,000, so we would deal with this by calculating the standard error. The standard error is going to be 30 divided by the square root of 1,000. Okay, I'm not sure what that is. Let's see what that comes out to. Okay, that's 30. Let's see, square root of 1,000. Square root of 1,000 is 31.6 roughly. Okay, actually I would probably use Excel to do. Let me pull up Excel. Again, there's Excel all over again. Okay, let me leave that there and bring up Excel here. Okay. Okay, so let's see where we are. Okay, so our sample size is 1,000. Our average weight is 100, X bar is 180. Our standard deviation for our sample, our standard deviation, you'll notice I'm not using sigma, is 30, right? And I want to go ahead and calculate my standard error. Now, normally, to calculate my standard error, I would need to know the population standard deviation. But this sample size is so big, I'm going to assume it's the same thing as the standard deviation of our sample. So that's equal to 30 divided by the square root of 1,000. What do I do now? Square root D50. Yeah, that looks right. Right? Yeah, that's right. Okay, so our standard error is basically roughly 1. So if I want to calculate my 95% confidence interval, what is my 95% confidence interval? Well, the lower limit, lower limit of our confidence interval is going to be equal to the mean from our sample minus 1.96 times our standard error. It's going to be equal to 178.14. And the upper limit is going to be equal to X bar plus 1.96 times our standard error. So our 95% confidence interval for the true mean weight of adult men in DeKalb County, where's that, Georgia? DeKalb County, I have relatives in Georgia. The average weight of males in DeKalb County, Georgia is about 400, but that's a whole other thing based on my relatives. But at any rate, so at any rate, they eat a lot of pasta down there and grits. But at any rate, they grow them pretty big down there. So at any rate, 95% confidence intervals between 178 and 181. So now we have some level of certainty. In other words, we have some measure that tells us how certain we are of what their average weight is. 99% confidence interval, we would do exactly the same thing, except instead of using 1.96, we would use 2.58. For a 90, what is a 90? Now, if the samples, I'm going to do that because it brings up an interesting issue here. So for a 99% confidence interval, right? What's it going to be equal to? It's going to be equal to, let me bring this up a little bit. It's going to be equal to 180 minus 2.58 times, right? And it's going to be equal to 180 plus 2.58 times our standard error. Oops, I missed it somehow or other there. I forgot to put an equal sign in there. Let me click in there. I'm leaning my palm on there. That's why it's not letting me write in there. Equals times 2.58 times standard error. Comes out to 170. Notice how this is wider now because we have a higher level of confidence that we've captured the true population mean between these two. Well, now what about if I reduce the sample size? Okay, and instead our sample size is 100 instead. Let's see what that's going to do to our confidence interval. What do we think it's going to do? Well, it lowers our level of confidence, right? It's a smaller sample size, right? We're not as confident when we have a smaller sample size. So what else is it going to do? Well, because it's a smaller sample size, my standard error is going to be a bigger number. And since it's a bigger number, when I multiply it by 2.58, I'm going to get a bigger margin of error and a wider distribution. Let's test that theory. Equals 30 divided by the square root of, instead of 1,000, this time 100. Yep. Okay. And that's equal to 3 now instead. Quite a bit different, right? So our 99% confidence interval is going to be equal to 180 times 2.58. Now for this smaller sample size, plus, minus in this case, times 3. And it's going to be equal to 180 plus 2.58 times 3. Okay, and it's wider. Again, from the same population, we get a wider 99% confidence interval because we were working with a smaller sample. Okay, and if it gets much smaller than 100, we got a problem here because, yeah, it's even wider, but not only that, but now we're less comfortable saying that we know the population standard deviation because our sample is getting so small that our level of certainty about that. So now we got two levels of uncertainty, a mean and a level of uncertainty about the standard deviation as well. So we're going to need to, as we move forward, we're going to need to adjust for that. In other words, I'm going to, since if my sample size gets really small, let's say my sample size gets to 20, really a pretty small sample. How, I want to calculate a confidence interval. I need to calculate a confidence interval. How does that affect me? The way it affects me is that now I can't be as sure that I understand what the population standard deviation is, and my margin of error is less certain. So now what I have to do is make that margin of error bigger in order to accommodate that extra uncertainty. Okay, and we're going to get to how we do that pretty shortly. Okay, so let's go move on to this next problem. And you guys remember when we talked about the binomial distribution? Okay, I had to bring up that ugly affair again, but I'm forced to. The binomial distribution is basically a variable that can have two values, yes or no, male or female, so on and so forth. So in this problem, a major metropolitan newspaper has a random sample of 200 voters. They ask them whether they are planned on voting for a new bond act. 55% said yes. In other words, let me think about this, 55%. 110 people said yes. 90 people said no. 55% yes, right? That level, that's a probability. That's a p-value. That's a percent. Let me put it this way. It's a proportion or a percentage. 55% of this sample say that they're going to vote for this. You remember that we had mentioned that when we were looking at that, let me bring this back up again. A while ago, we looked at that thing called a Galton machine. And in the Galton machine, we were dropping balls down from that were hitting little pinballs, hitting bars and bouncing back and forth. Half the time they turned left, half the time right. So those balls would pile up, even though it was a binomial, how many lefts, how many rights, right? By the time it reached the bottom, maybe 10 rows, it had made 10 turns, either to the left or to the right, right? And most of the time, most frequent outcome is it would make 5 to the left, 5 to the right, just randomly, right? And then, less often it would make 4 to the left, and less often 3 to the left, and 2. And pretty soon, the number of balls that piled up would be smaller and smaller as you went to the outside. In fact, we saw it formed what looked like a normal distribution. It's really a little bit different. It's a binomial distribution, really. But what we call it a normal approximation to the binomial distribution. We're going to assume for our purposes that when we do a probability thing, a percentage thing like this, a binomial distribution, we're going to assume it has certain properties that are similar to a normal distribution. Okay? So the middle of our normal distribution, instead of being a mean, instead of being x bar or mu, what is the middle going to be for us for a proportion? It's going to be a p-value, a percentage, right? Now, I'm going to call that p-value p cap, right? I'm going to call p the percentage for the true population. The percentage of people if they had surveyed everybody in the city about whether or not they like the newspaper, that would be the p-value percentage. In other words, maybe it's 57%, maybe it's 45%. That would be the p-value. Now, the p cap is going to be the proportion from this sample, right? So if you see p cap, it's the same as x bar. And remember, what did I call those things? What did I call x bar besides the mean? I called it a certain kind of estimate. I called it a point estimate. It's the point that we think is the middle, right, or the average proportion, right? So the way we get a point estimate with a numerical variable is we call it x bar. That's our point estimate, the middle, right? Our point estimate for a proportion is p cap. Okay, so that's our point estimate. We're going to use it exactly the same way. We're going to look at how these different. If we went back and sampled another 200 people, maybe this time I got 52%. Another 200 people, maybe this time I got 57%. Maybe I got 45%. And I redrew this new distribution based on these repeated samples, just like I did with the mean. Now I'm going to go back and my p cap, right, for this particular sample was 0.55. Right? 55% of the people said that they liked, I forget what they said they liked the newspaper or whatever it was. Now, what do I need to understand this distribution, how spread out this distribution is likely to be? I need a standard deviation or a standard error, basically, right? Now, how do I calculate that? Well, I'm not going to go in the lecture. It's probably a little bit of theory on how this is calculated this way, but based on probability theory. Right? But I'm just going to go dive right in. And I'm going to say that the standard error or standard deviation for a distribution that's a binomial, a proportion, is going to be equal to the square root. This is going to cover everything, by the way. Square root of p, right? Actually, p cap in our case, times 1 minus p over the sample size. Right? So our purpose is now, what is that number going to be? The standard error is going to be equal to, let's say, square root of 0.55, right? This is painful doing this way. I have to find my pen and my tablet. 0.55 times, whoops, I'll put that in percent, times 1 minus 0.55, which is 0.45, right, over the sample size. I think we said sample size was 200, right? Okay. So let's calculate that. And I'm going to use Excel to calculate it. You could use a calculator if you want. Okay, here we go. Here's Excel. Okay, so my standard error, I'm sorry. Okay, equals. You guys can do it on your own. Go ahead, you should do it. I say question there. I'll get to the question in just a second. 0.55 times 0.45 divided by 200. Okay, and then I got to find the square root of this whole thing. So then I'm just going to go in here and surround this with, I'll tell you what, I'll do that first. And that comes out to that value. And now I'll find the square root of that value. Do it in 2 steps. Okay, and the square root of that is 0.035. So that's my standard error. That's that's the spread on my distribution. My standard error is equal to, let me go back to that. My standard error is equal to 0.035. 0.035. Well, now let's calculate a confidence interval for our point estimate, which in this case happens to be a proportion. So how do I do it? Well, instead of X bar, I'm going to say P cap plus or minus 0.55. Excuse me, I got away from me a little bit. P cap plus or minus the Z-score I'm going to use, right? Times the standard error. Z-score is based on what level of confidence I want. Let's say I want 95%. So what is that going to be equal to? It's going to be equal to 0.55. I'll start with minus 1.96, just like before, right? Because we're saying it approximates a normal distribution, times my standard error, which in this case is 0.035, 3.5%, right? I'm going to call it 2 you can calculate exactly what it is. I would too. If I had Excel, I would calculate exactly what it is. So what's the lower limit here? It's 3 times 2 is 6. 0.55, so it's between 0.49, right? And the upper level is going to be 0.55 plus 1.96, right? I'm going to change that to a plus 0.07, right? 2 times 0.07, so it would be 0.48, right? And the upper limit would be 2 times 3.5, it would be 7%. Added to the 55 would be 6.62. So I'm 95% confident that the true proportion for everybody in the city, the entire population, is between 0.48 and 0.62. Well, what was the question here again? Let's go back and take a look at this question. Okay, what was the 95% confidence interval? Okay, what's the margin of error for this poll? Well, you want to know something. The margin of error for the poll was what? What was the margin of error? How much did we add and subtract when we multiplied the 1.96 into 3.5? We added and subtracted 7%, right? 3.035 times 1.96, 7%. The margin of error for this poll is 7%. In a sense, it's a little bit, they do a few other tricks and stuff like that. In a sense, if you went out and asked people, do you plan on voting for Donald Trump this year? And 49% of them said yes. You would use this logic to calculate the margin of error for your poll, right? If you would use the same, you'd calculate standard error. Actually, if I can find some polling numbers, I'll show you they actually do it. They cheat a little bit. They use when they use the standard error, they use 0.5 all the time because it's the worst case, so that they can say, you ever notice on a poll, one candidate might have 35%, another candidate might have 48%. So, but they always say, the margin of error is 4%. They always use the same margin of error. That's there's a reason for that. Don't worry about that right now. I'll show you that when we get a few minutes. I'll show you that because it's kind of interesting that they do that a little bit of a cheat that way. So what's the margin of error? 7% is the margin of error for this poll. So like in other words, so here, let's see. The simple they asked whether they planned on voting for a new bond act. Do we know for sure if this bond act is going to pass now? Are we 95% certain it's going to pass? Well, let me put it to you this way. If we were 95% sure that, let's say that the margin of error had only been 2%, then we would be 90% certain, we would 95% certain that the percentage of the population that was voting for this was voting positively for this was between 53% and 57%. So are we pretty sure, are we 95% sure it's going to pass? Yeah, because we're 95% sure the proportion of the population is between those two numbers. In this case, we're 95% sure the true proportion that's going to vote for this bond is between 48 and whatever it was, 57, 50, whatever. Are we sure now? No, we're not, because because it could be below 50%. We're not 95% sure. If I had said we would have been satisfied with 90% sure, it might have come up between 51% and 58%, let's say. So we might be 90% sure, but we're not 95% sure because 95% overlaps that critical value for us. 50% is inside of our confidence interval. I can't say that the probability of getting less than 50% is outside of our confidence interval, right? So we're going to start to learn how to use these probabilities to decide whether or not a candidate is going to win, a candidate is going to lose, the level of certainty we have about our judgment, and also, for instance, if we compared one group, say people in this town to people in a town upstate, whether or not they would be voting the same or differently, whether their confidence intervals would overlap or not overlap, whether their confidence intervals are close to one another or whether they're so different that it makes us really think that the true population proportions are different for those towns. Okay, so is there a function or an Excel that has the ability to calculate the values we just did for the confidence interval, or is manually? That's a good question. No, I don't think so. I think you're gonna. Well, let's see. I've done it this way for so long. I just let's see, confidence. Let's see what confidence tells us. Parentheses. If we put in 99, let's see, 99. Let's say we're talking about a 95% confidence interval. Let me see if this will work here. 0.95. Maybe that's what alpha is. Oh, maybe not. Maybe alpha is. I should look it up, right? I should click on this. Well, let me give this a try. What did we just do? We just did the standard deviation was for this was how much was this one? 0.035 or something.
Oh yeah.
Comma 0.035 comma, and the sample size was 200. That's what this gives me. Nope, that's confidence. I should actually look at. Want to know something? I'm glad you brought that question up. I'll check out the different functions and find out. Let's see. It's available with compatibility. See alpha. More help on this function. Okay, alpha is the significance level used to compute the confidence interval equals 100 times. In other words, alpha of 0.05 indicates a 95%. Oh, so alpha should be 0.05. Okay, 95% confidence interval. Alpha represents the probability of being wrong. So if you're 95% confident, it means you got a 5% chance of being wrong, right? So that's the way they want you to use this function. And in fact, this is going to make sense to you because alpha literally is that kind of that kind is used generally in statistics that way, as some of you guys know already. I'm going to go back in here. I'm going to change that to 0.05. Okay, does that look familiar now? No, it doesn't. 0.05.
It's 7 o'clock.
Is that what we got before?
0.48, the interval.
Oh, for the margin, yeah, for the interval, for the margin of error? No, that's small. That's 0.04. Something's wrong there. Let me try it with one of these others, with one of the non-binomial distribution. Okay, so for instance, let's try it here. Let's even go up here. Okay, let's try it here. Oops. See what it gives us. Equals confidence parentheses. It's so easy. It's so easy to get me off on a tangent. I'm telling you. Confidence equals 0.05, comma, standard deviation. Now, is that standard deviation of the population? I guess it is. Comma, and the sample size here was 100. Close parentheses. 5.87. Okay, did we use that somewhere? Confidence interval is a range of values. Mean, yeah, I think that is. This is going to be our margin of error. I think that's what they mean by confidence. I'll check that. I'll check that, and we'll talk about it next week. But it does look like you have more functions available to you that you can use. And basically, if you wanted to change this to the 99% confidence interval, you would just subtract. You would just change that from 0.05 to 0.01, and it got wider. Okay, does it work? Want to give it a try? Equals the mean. We don't need the mean. We just need standard error. Standard error. No. Standard error divided by the. Actually, we got standard error. It's just going to be 2.58 times our standard error. Yeah. It's, I mean, you remember that that 3 I think is really rounded. I don't think it's exact. I don't recall. Oh, it is exactly 3. So yeah, basically we're getting same answer here as we get here, right? 7.73, 7.74. So it's basically calculating the margin of error. They call it confidence, right? The function is called confidence, but what it's really calculating is the margin of error. Let me just do it again. Equals, right? Confidence, right? Parentheses, and it's asking number 1 for alpha, the probability of being wrong. Probability of being wrong for a 99% confidence interval is 0.01, 1%. Probability alpha, the probability of being wrong for a 95% confidence interval is 0.05, comma, the standard deviation, right, for the sample, which is 30, comma, the sample size is 200, close parentheses, and it returns what I would have gotten if I did 1.96 times, is that right? 1.96 times standard error. That is 2.58. Oh, actually, I just did the 90%. This would actually be, no, I did the right one. Yeah, you know what? We shouldn't play with this because I'll just I apologize for confusing the whole issue by going off on a tangent. I'll tell you what. I'll look at it next week. I'll clarify it, okay? So that I'll actually have a couple of examples, and I'll see if there's some other functions that are built into Excel that can clarify this, that can speed this up for you. But to tell you the truth, I've normally just calculated it manually because it's just just a simple calculation. Okay, so let's see where we stand now. Now I have a couple of like this is left over from the fall, so you have to take this with a grain of salt here. But I try and relate it to a kind of a pseudo real calculation here, right? Basic epidemiology, okay. So in this case, we're looking at zombie public health, right? So we want to calculate the confidence interval for sample means. Zombies' primary food sources: brains and spinal cords. Diet high in protein and low in carbohydrates. Serocholesterol levels are measured. 25 randomly selected adult zombies The mean of the sample is said to be X bar is equal to 151.4. The population standard deviation, sigma, for zombies is assumed to be the same as for living humans, 38 milligrams per deciliter. Okay, so now calculate the standard error for zombie cholesterol, calculate 95%, 99% confidence interval for mean cholesterol for all zombies. Okay, so a little tongue-in-cheek, but basically what we're looking for here is you have a mean, a point estimate, 151. You have a estimate of the standard deviation of the population, 38, and you have a sample size. Sample size happens to be 25. So our job here now is to calculate the standard error and a 95 and a 99% confidence interval. So I'll give you guys give that a try on your own. Ignore all these other folderol that I put on here, okay, in an effort to maintain some people's interest here. Okay, you guys at home, give that a try also. Okay, I'm going to get started to catch up to you guys. So first thing I'm going to do is calculate the standard error. Okay, well the assumption that we're making here is that we're assuming that we know the population standard deviation. By all rights, we're kind of stretching with a sample size of 25. We're stretching the truth a little bit, but the reason why we're saying it here is we're justifying it by saying we know the true populations, or we have a good idea of the true population standard deviation for a similar group, living humans. So we're going to assume that it's the same for this group, even though our sample was small. So our standard error is going to be equal to 38, right? Standard deviation divided by the square root of the sample size, which is 25. Okay, and it turns out to be 7.6. So our 95% confidence interval is going to be equal to the mean minus 1.96 times our standard error, which is 7.6. So 2 times 7.6 is roughly 15. We're going to be adding and subtracting a margin of error of 15 from our point estimate for the mean, which is 151. That's 136 equals 151.4 plus 1.96 times our standard error. So our 95% confidence interval for the true serum cholesterol level for the entire population of zombies is 136 to 166. We're 95% sure that that's what the confidence interval is. Okay, so let's look at the next one. Proportion of male. Okay, here we go. Let's see. Now this is one where we're working with a proportion. Okay, careful study of zombie movies. It appears that zombies are predominantly male college students. Here you can see one. There's one, the recent graduate from the School of Public Health there on the left. The proportion of male college graduates in the general population in the United States is known to be 0.48. Okay, you wouldn't know that from this class, right? Looks like the male population of graduate students from this class is about 5%, right? Right? So, isn't it unusual, right? I mean, I normally, even during the classes during the year, yeah, maybe it's about a 60-40 split. There's probably more females than males. But this class is only one guy, yeah. Well, I guess the guys don't like that going to summer school, I guess.
And even my class, my future nutrition class.
Oh, yeah, same for summer class also?
Only girls. No, I'm talking about the nutrition master.
Yeah, yeah. Well, maybe it have something to do with the major, maybe, possibly. But I'm kind of, there's people here from all different courses and schools and stuff like that. So it seems so we have a unusually different sample. Yeah, I guess. So at any rate, random sample of 100 zombies. Found 58 of this sample were male. Okay, so what is the 95% confidence interval for the true proportion of male zombies in all such movies? Based on this, can you say with 95% certainty there's a difference in gender distribution of zombies versus the living? Okay, so what we're looking for is in this sample, we got 58 males out of 100. Is that different enough from 48 out of 100 for the general population for us to say that's really true for the entire population? There's more males than there are in the general population. Okay, so let's give this a try. And in order to do this, this is a proportion now. So 58 out of 100, my P cap is 58 out of 100 or 0.58, right? So let's see how that, if we took repeated samples, how that would be distributed. Okay, so here we are going to take this. So our P cap, or our point estimate, is 0.58. Our standard deviation, or our standard error rather, is equal to the square root of 0.58, right, times 1 minus 0.58, which is 0.42, divided by the sample size, which was 100. Okay, I got to put this in parentheses here so it calculates that first, I guess. I think I may not even need them there, but yeah. And I got to put this whole thing in here, otherwise it will I got to put parentheses on the whole thing, otherwise it will just do the square root of the top part. Okay, so I'm going to hit. Yeah, I got the same thing, almost 0.05, 0.049. Okay, so that's my standard error. So now I have to calculate my margin of error. What's my margin of error going to be? Well, what level of certainty do we want? What confidence interval? 95% confident. So our margin of error is going to be equal to 1.96 times 0.49, right? That's our margin of error. That's the amount that I'm going to add and subtract to my point estimate. So my 95% confidence, see, I kind of like added an extra step there. I didn't do it all in one step. Our margin of error is going to be, our confidence interval is going to be equal to our point estimate, 0.58, minus our margin of error, which was 1.96 times the standard error, or is equal to 0.58, no, excuse me, it's equal to 0.58 plus my margin of error, right? So it's between 48% and 6. We're 95% sure the true populations of zombies in the movie is male zombies in the movies is between 48% and 67%. Well, what were we comparing it to? 48%. So we're right on the cusp, right? It looks like maybe there is a difference that the 0.48 is outside of our confidence interval almost. Actually, in fact, it is a teeny bit outside of our confidence interval, right? So with the assumption that's a little teeny bit outside of our confidence interval, we might be willing to say we're 95% sure that the proportion of males for zombies is different than the proportion of males for the living population, right? So it's just outside of that range, right? So kind of close, but we're outside rather than inside that range. Okay, so that's really what we're doing here. We're trying to find the mean. We're trying to evaluate what our level of certainty is with that mean, or that where the center of that population is. And we're going to wind up doing some more accurate evaluations of this going forward. So now what I would like to do now is I just want to introduce one other idea. And in order to do that, I have to pull up a table here. Okay, this is something called a t-distribution. We're going to be talking about the student's t-test. It has nothing to do with students. It's a guy who used the name student as a student. T. I'm just going to go online and grab it online. I got a copy. Oh, I might have it on Blackboard. Yeah, it's opened up already, I guess. Do I have a t-table on Blackboard? Yeah, I do. Okay, I'm gonna go to the list. I might be willing to just say, I'm going to just use that as the population standard deviation when I do my confidence intervals, right? But if I have a smaller sample, I have less and less confidence, so I have to adjust for that. If I want to use the sample standard deviation, I have to adjust, make my confidence interval wider to accommodate for the fact that I'm not that positive, and as the sample gets smaller and smaller, I'm even less confident how well I know the true standard deviation of the population. So the way that we adjust for that is, instead of using a Z-score, a Z number, we use something called a T-score, right? So for instance, if I got an infinitely large population, the sample, right, infinitely large population, I go down to the bottom of this table. If I look down at the bottom of this table, you see it there, infinite. If I look in the middle column, it says confidence level 95%. In other words, 2.5% in the right tail and 2.5% left tail, right? If I go down to the bottom of this column, it says use a t-score or a z-score of 1.96. Hey, there you go. I have the old population. I can use 1.96. But now, as my sample size, this represents, column on the left represents the sample size. Slightly more complicated. They call it degrees of freedom. It's really the sample size minus 1. We do that frequently in statistics. Let's not worry about it right at this moment, why we're doing it here. But as the sample size gets smaller, what happens to the value that I have to use for t instead of z? Now I'm going to use t in place of the z. It gets bigger, doesn't it? So if I have a sample size of 10, instead of multiplying by 1.96 times the standard error, I multiply by 2.22, 2.23. It makes my confidence interval wider and makes up for my level of uncertainty with the standard deviation. So when you use a small sample to estimate the standard deviation of the population, you can't use the Z-score for your confidence interval. You have to use T-score times your standard error to calculate your margin of error. So for our sample, when we did that sample of size 25, right, size 25, we would have had to multiply by 0.206 instead of 1.96. And if we wanted to calculate the 99% confidence interval, we'd go over here into this column. And for a sample of 25, instead of 2.58, we'd multiply by 2.79 and so on. So we use this table to give us a t-score to make up for that level of uncertainty. So next week, we're going to be working with examples of the confidence interval and something called a t-test, where we're going to be working with true samples, where we're going to be really calculating confidence intervals and other things based on the true sample, what we would really have in real life, which is a mean and a standard deviation based on a sample. A sample usually not enormous, so we're forced to go to this t table instead of using the z table. Okay, notice that it only gives you the values. You don't have to worry about that big distribution tape, it only gives you the ones you really need: 95, 99, 90, and the sample size, right? Or a measure of the sample size, degrees of freedom, 1 minus the sample size. Okay, I'm quickly running out of power here. So I am going to end this session.